Hi, I'm Cameron White, Senior 3D Software Developer at KineFX. In this series of videos, we'll be doing a deep dive into agent primitives, which are the foundation of the crowd tools in Houdini, how the crowd characters are represented and instanced. And so we'll be focusing primarily on how agents work and the process of creating agents, building the agent definition, setting up the geometry, animation, and so on that'll be used in a crowd. And so we'll be focusing much more on that versus things like the crowd solver and the simulation side of things. Along the way, we'll also be covering some of the new features for the crowd tools in Houdini 19, things like improvements to the geometry variation workflow, as well as also showing how the KineFX tools for rigging at the SOP level can also be very useful for setting up crowd characters. So in this first section, we'll start off with a general overview of agent primitives and the different parts that make up an agent, and then jump into how to create and manipulate agent primitives, set up their rig or skeleton, and then finally how to effectively deal with caching. So for crowds, we need to be able to represent a large number of characters efficiently, so say in the tens to hundreds of thousands of characters. And so the way that we represent a crowd character needs to keep memory usage as low as possible and also be optimized primarily for performance rather than complete flexibility compared to, say, how a character would be represented in SOPs for KineFX, which is more for general purpose rigging. So in a crowd, you'll often have a lot of instances of the same skeleton, of course, with different animation and poses so that there's visual variation. And similarly, often the same geometry shapes are going to be instanced throughout the crowd, but assembled in different combinations or with different textures applied so that there's some variation there. So crowd agents definitely need to be able to take advantage of this and store instance data like the skeleton and rest geometry and so on, and reuse that between different characters in the crowd. But also, of course, there's going to be some unique data per agent that we can't avoid storing, right? Things like the current pose, what geometry shapes they're supposed to be displaying, and so on. And also related to this, if we were to generate the final deformed geometry for an entire crowd, that would be extremely heavy. You probably wouldn't want to be storing this on disk because it would take up a ton of space. So we want to be able to deform the geometry just when it's requested at render time in order to be able to get good performance. And so in Houdini, taking all of this into account with wanting to be able to store a lot of instance data and also generating geometry just only when it's requested, the solution for this is to use a packed primitive. So as a quick refresher, packed primitives are a set of primitive types in Houdini, which each store a transform and some information for how to produce geometry when they're unpacked. So this is a form of delayed loading of geometry, where the geometry is only generated when it's requested by something. Every packed primitive has a single point that's attached to it, so positioning this point will just adjust the translation of the packed primitive's transform. So just as a couple examples, one common example of a packed primitive that you might have seen before is a packed geometry primitive, which you can generate with the packed SOP or the copy to point SOP and so on. So this type of packed primitive just stores a reference to some geometry in memory. So unpacking it just returns that geometry, but with the packed primitive's transform applied. That reference is shared between the copies of the packed primitive. So this is a really efficient way to represent instanced copies of geometry that each have their own transform. Another example of a packed primitive is a packed disk primitive, which instead just stores a file name. So when the primitive is unpacked, that causes it to load the geometry from that file on disk, also applying the packed primitive transform. And so this gives you a way to delay load geometry from disk. So agent primitives are just another type of packed primitive, but they're designed to represent an instance of a character. So unpacking an agent, so when its geometry is requested, we want that to produce the final deformed geometry for the character. So in order to do that, that means that the agent needs to have access to a skeleton, a current pose, the geometry that should be deformed, and so on. And so that means that agents do have to store a lot more pieces of data than something simple like a packed disk primitive would. And since we want to be able to store instance data between different characters, that means that the agent is going to have some shared data, things like the rest geometry shapes and skeleton hierarchy and so on that are going to be common to a whole bunch of instances of an agent, as well as unique data per instance, things like what its current pose is and standard packed primitive stuff like what its overall transform is going to be. I also just wanted to quickly point out a useful page in the documentation, which is the agent primitives page under the crowd section. And we'll be covering most of the information on this page during the videos, but it is a useful page to refer to if you want any additional details on agents. And it has a good overview of some of the APIs that are available in Vex and in Python for manipulating agents. So it can be a useful page to take advantage of. So all of the shared data for an agent primitive is what we refer to as the agent definition. So this is shared between all of the copies or instances of an agent. So you'll just have one agent definition for each type of character in the crowd. We'll be going in depth into each of these, but just as an overview, all of the different parts in the agent definition are the rig, which is defining the skeleton hierarchy, the rest pose, and also defines channels, which are used for things like blend shapes. There's the shape library, which has all of the REST geometry shapes that are available for an instance of an agent to use. There's a list of layers, and each layer defines a set of shapes that can be assigned to an agent, along with things like what deformer to use. There's animation clips, which are used just to drive the pose of an agent. And then transform groups define a group of joints or channels, and they're used typically for things like applying layered animation clips to just, say, the upper body of a skeleton. There's the metadata, which is a dictionary that can be used to store custom user data in the agent definition. And then finally, in the HDK, it's also possible to define your own custom data items that live in the agent definition. So along with the shared agent definition, each primitive then, of course, also has some of its own data that's unique for every single instance. So just like every packed primitive type, it has an overall transform, which is going to be positioning the agent in world space. So one thing that's a little bit different from other packed primitive types that I wanted to point out is that all of the standard point instancing attributes like orient, M, V, and so on that you might use with, say, the copy to point swap will also affect the agent primitive's transform. So this lets you kind of treat it a bit more like a particle where you can just manipulate some attributes on the point and influence its orientation. So just as a little quick example here, I've just got a crowd of agents here, and then I'm using the attribute adjust vector swap to just randomly assign different values to the V attribute. You can see the effect there. And you'll notice that this is affecting the agent primitive's overall transform. And the reason for this is that the point instance transform option, which every packed primitive has but is off by default, is enabled by default for agent primitives. So if we look in the spreadsheet at the point instance transform intrinsic here, you'll notice that it's set to 1. And so changing attributes like V and orient and so on will affect the transform of the packed primitive that the point is attached to. And so if I turn this off just with a wrangle here that sets it to 0, you'll notice that that means that the V attribute no longer has an effect on the agent's transform. So this is something you can also use with other packed primitive types. It's just not enabled by default. So if I take a packed geometry primitive here and assign a V attribute to it, you'll notice that it doesn't have any effect on the orientation. And that's because the point instance transform intrinsic here is just set to 0. But if I turn that on, so just set this to 1, you'll notice that it does actually now affect the orientation of that packed geometry primitive. So having this on by default for agents is very useful because often we want to be able to just do stuff with the particle of the agent and have that influence the actual orientation of the agent packed primitive itself. So along with the overall transform that's attached to the agent, there's also some per agent data that's specific for agent primitives. So things like the current pose, which has a transform for every joint and also values for any channels that are defined on the rig. So we can see that here, of course, each agent has its own unique pose that's just a random sample from its clip. And this is also accessible in the primitive intrinsics with things like the agent local transforms or world transforms intrinsics. Obviously, inspecting a very long array of matrices in the spreadsheet isn't particularly nice, but it is accessible there. And then there's also some intrinsics that let you read some of the data from the agent definition. So things like the agent transform names intrinsic lets you inspect what all of the joint names in the rigs are, and so on. You can also inspect, what clips are available in the agent definition, and also things like what layer names and shape names, etc., are available. Along with that, each agent can also have a list of animation clips assigned to it, which are just used to drive whatever its current pose is based on sampling those clips at a particular time. And then to determine what the geometry of the agent is, it can also have layers assigned to it, which determine what shapes and what deformers are being used for the display geometry of the agent. And then similarly, you can also change what geometry is being used for the collision geometry and bounding blocks and so on of a particular agent instance. So for manipulating agents, there's a few different ways to go about it if you're building custom tools. So as we were already seeing, there are primitive intrinsics available for agents. These are limited mostly to accessing the per instance data, so things like the current pose of the agent or what clips are assigned to it. And then just in a limited manner, inspecting some of the data that's in the agent definition, like what joint names are in the rig and so on. More likely, though, you'll probably want to be using either Python or Vex, which have much better APIs for dealing with agents. Most of the crowd nodes in Houdini are actually HDAs that are implemented in Vex or in Python, and so the APIs are really extensive and let you do almost anything you need to be doing with agents. So for Vex, all of the agent-related functions are in the documentation under the crowd section. And the functions that are available are geared more towards things that you typically be doing in a solver, running over all the agents in parallel. So you can do things like reading or modifying all of the per instance data for an agent. So for example, you could use agent local transform to read what the current local transform of a joint is in the agent's pose, and then things like set agent local transform for actually modifying the current local transforms for an agent. And then there's also a lot of functions available for reading data out of the agent definition. So an example, agent clip sample lets you take any clip in the agent definition and sample the transforms in it at a particular time. On the Python side of things, there are equivalents to all of the VEX functions, but you also have a bit more ability to modify the shared data, so the agent definition. So for Python, there's the agent class, which represents a single agent primitive. So this is a subclass of the pacprim class. And so similar to the VEX functions, you can access all of the per instance data for the agent. So things like what its current transforms are, what clips are assigned to it, and so on. But you can also access the agent definition and modify the agent definition. So you can add new clips and layers to it. You can create a new rig from scratch if you want to build a transform hierarchy directly through Python. You can create a new shape library from scratch and so on. And then for an agent, you can use the set definition method to actually change what agent definition it's referencing. There's also some really useful utility functions in the crowds module. So one I really wanted to highlight is the replace agent definitions function. So this is for the common pattern of where you have a Python SOP that's taking as input a whole bunch of agents and you want to make some change to the agent definition. So this lets you basically just find all of the unique agent definitions that are in the input, make a change to them, and then carefully replace all of the agents in the crowd to reference the new version of their agent definition, making sure that all of the agents that were all combined referencing the original agent definition are all rewired to reference the new version of the agent definition, keeping all of the shared data shared. So next, we'll take a look at how to go about actually creating agents. So there's a few different approaches you can take depending on your workflow, but the two main ones we'll be talking about are the agent SOP and the agent from rig SOP. If you do need to create agents from some custom file format, you can do that through Python with the agent definition class that I just mentioned, or in C++ through the HDK is possible as well. So first we'll look at the agent SOP. So in this case here, I have it set to import from an FBX file. So the agent SOP will create an agent primitive and build its agent definition from some source character, which based on the info menu can be something like an object level character rig in the scene, an FBX file that's on disk, or a USD file that's on disk or in LOPS. And then the agent definition cast option is a bit different, and we'll talk about that in a subsequent section. So this will build basically a complete agent definition for you from all of the data that the character asset has. So it'll create the agent's rig from the skeleton on the source asset. It'll import all of its geometry into the shape library, and then it'll create a layer based or with all of the new shapes that were added into the shape library, and then also create an animation clip from the animation that's on that source character asset. This will also play back the animation for you by default because of the clip offset parameter here, which is just set to play back the clip based on the current time. And so this is a really quick way to just import an entire character as an agent. This can be a bit of a black box though. So if we wanted to, say, make some edits to the skeleton or to the geometry before it got actually added into the agent, you don't really have a chance to do that because it's importing it directly from disk. Once you have the initial agent definition, though, if you want to keep adding some more data to it, like some more animation clips, you can just use some additional agent-related SOPs for doing that. So for example, the agent clip SOP lets you import some additional animation clips from various external sources and add those onto the agent definition. And then similarly, if we wanted to add some more geometry, we could use the agent layer SOP. It both lets us import some additional shapes into the shape library, but also add some additional layers to the agent. So this is the basic workflow. Once you set up your initial agent primitive and agent definition, you can keep using more SOPs to add more things into the agent definition, like animation clips and geometry and so on. And then once you finally built your agent definition, then you proceed ahead with populating a crowd and getting on with the rest of the crowd shot. So next, we'll look at the agent from RigSOP, which creates an agent from a SOP skeleton, like what you would have from the KineFX tools. So in this case, we'll use the FBX character import SOP to import the same asset. So this is the KineFX FBX import SOP. And so this gives us three outputs. One is the skin geometry, which has the bone capture attribute. And then the second output is the bind pose skeleton. And then the third output is the actual animated skeleton. So the agent from RigSop takes as input only a skeleton. So this is definitely a much less monolithic node than the agent SOP. It's not dealing with importing geometry or animation. It's just going to build the rig out of the transform hierarchy from this skeleton geometry. And so the idea here is that you can just use subsequent nodes like the agent layer SOP, the agent clip SOP, and so on if you want to import the geometry, just like you would have with the agent SOP if you had to do any further addition of animation clips. So on the agent from RigSop, there's a few parameters to go through. So the agent name parameter just initializes the value of the agent name point attribute, which is just a convention that we use in some of the crowd tools. So that if you have multiple types of characters in your crowd, this is just an easy way to identify what a particular agent primitives type is. And then next, the agent from RigSop is basically just building the transform hierarchy for the agent and also setting its rest pose. And so these parameters control how it actually determines what the rest pose is. So you can load the rest pose from a rest transform attribute that's on your SOP skeleton. In this case, we don't have that. So it'll just be cooking the SOP skeleton at this rest frame and using that as the rest pose for the agent. And then finally, there's also an option for whether to create a locomotion joint, which is on by default and is usually what you'll want to have if your animation clips that you're going to be adding downstream have locomotion in them. And then finally, there's a couple options here, which we'll talk about more later, but are for just setting up transform groups in the agent definition. So this lets you take point groups that are on the input skeleton and turn those into joint groups in the agent definition for use with layering animation clips and so on. And so once we've got this, we now have our agent primitive. You'll notice that it doesn't have any geometry because we're going to use subsequent nodes to do that. But if you hit W in the viewport, you can see the wireframe representation of the agent skeleton. So then we'll continue on ahead with the setup and just quickly use the agent layer SOP, which we'll be talking about in more detail in a subsequent video, to import the skin geometry from the KineFX node. And then finally, we'll also use the agent clip SOP to import from a motion clip from KineFX to load in that animation. And then finally, we can populate our crowd and play back some animation. So one nice thing with the KineFX workflow here is that because the data we're importing is just living in SOPs, it's really easy to make some modifications to it before we add it into the agent. So just as an example here, with the skeleton that we're adding, there are a lot of joints here on the fingers, each individual finger joint, and we might not actually want that for a crowd agent. If it's going to be far in the background, we might not actually notice that animation, and reducing the number of joints is a good thing for performance and memory usage, right? Because every instance of an agent has a pose, which means it's going to be storing a transform matrix for every single one of these joints. So if we were wanting to do this with the agent SOP workflow, there wasn't really a good way to do that unless maybe we imported it into the scene as an object level rig and then made our modifications. But here we can just make some procedural modifications. So we can just use, say, a delete joint SOP. I'll turn this on and just delete those joints that we don't care about having in our agent. And then those joints won't be included in our agent skeleton anymore. So it's very easy to make these kinds of modifications to the skeleton hierarchy and so on before we import them into the agent. So it's definitely got some advantages with this workflow. I'll just turn that off for now. And so once you've actually gone ahead and created the agent, it's still very easy to convert it back to a KineFX skeleton if you want to do some round tripping between the KineFX tools and the crowd tools. So just an example here, once we've added our geometry, I'll just use the agent edit SOP to make some simple changes to the pose of the agent. So I'll just select this joint and rotate it a bit. And so if we want to convert this back to a KineFX skeleton, we can use the agent animation unpack the SOP. So if we set the output here to pose, this will just output the current pose of the agent as a SOP skeleton. So we're back to having polygons describing the hierarchy and a name attribute, transform attribute, and so on, like we have in the KineFX tools. And so this lets you take the agent's current pose back, but you can also optionally just output the rest pose of the agent as a SOP skeleton as well. And this is giving us back what our rest pose was configured as on the agent from RigSop. And then finally, there's a couple other options for converting agent clips back to motion clips, which are the KineFX representation for an animation clip with samples over time. So the agent animation unpack SOP is actually just a wrapper around the more general agent unpack SOP, which has even more options for what to do with extracting data from agents. So if we look at this, the default output mode here is to output the final deformed geometry for the agent, which in this case is, just a bunch of polygons. And you have some configuration options here for if you want to only unpack certain layers or shapes that the agent has assigned to it. And then if there's any nested pack primitives, you can also control how many iterations of unpacking are performed. As a useful debugging tool, you can also output some additional attributes describing the shapes that are assigned to the agent. So things like what shape deformer was actually used, in this case, linear skinning, what layer name the shape actually came from, and so on. And then similar to normal unpack stops, you can also transfer attributes from the agent primitive onto the unpacked geometry. And then similarly, you can also extract just the undeformed rest geometry from the agent if you want to, for example, get at the original shape from the agent, make some changes to it, and then add it back into the agent definition. The rest geometry option is the option to be using. So this just gives us our undeformed geometry. And then the skeleton output here is exactly what the agent animation unpack soft was wrapping up for us. There's some options here for what to do with joint transforms. So if we don't apply the joint transforms that the agent currently has, this will just give us the rest pose. And then if the agent was transformed somewhere in world space, so I'll just add a transform sop in here and just shift that over a bit. This option also lets us control whether we want to apply the overall transform to the agent or just output at the origin. And then the motion clipped output option is also exactly what the agent animation unpack SOP was outputting. And then the joints option is kind of related to the skeleton output, but instead of outputting the skeleton geometry with polylines that are defining the hierarchy, it just outputs a bunch of points for each of the joints. And this can be more useful for doing things like driving secondary effects, where you just want to have some points based on the agent's joint positions to drive something like dust or something like that from where footsteps landed and things like that. One useful option here is this filter option, which lets you only output points for, say, certain joints. So in this case, we could do something like star_r, and we just output points for the joints that are on the right side of the agent's rig. And then if there's actually a crowd of agents here, you can use this percentage option to only output points for, say, 10% of the agents. So this is useful for kind of scattering points throughout the crowd. So just to summarize some of the information we kind of covered in the demo about agent rigs, the rig consists of a few things. So there's the transform hierarchy, so what joints are available, what the parent-child relationships are between the joints, but it doesn't store the actual pose for an agent, right? Each individual instance of an agent has different transforms for each of these joints, but the hierarchy and structure of the skeleton is the same for every single instance. Along with that, the agent rig also stores the rest pose, and this is used in a few places. So it's used if it's, of course, requested explicitly, like what I was showing with the agent animation unpack SOP, but it also gets used just as fallback transforms whenever they're needed. So if an agent doesn't have any clip assigned to it and also doesn't have any pose assigned to it, the rest pose will be the pose of the agent. And then if you're, for example, loading animation clips that don't actually have animation data for every joint in the rig, the rest pose transform will just be used as a fallback there. And then finally, if there's any channels defined on the rig, which are used more for things like blend shapes, the agent rig defines what channels are available, what their default values are, similar to the rest pose. And then again, each individual instance of an agent has its own unique current values for whatever those channels are. So finally, once you've built your agent definition, you'll often want to cache it out. So one reason for doing this, of course, is to avoid redoing any expensive processing of the geometry or animation and so on, or loading really heavy character assets. But another workflow too also is being able to generate the agent definition once and then separately load it into multiple different scenes for a project. One other consideration too that might be a bit less obvious though is reducing the size of the BGO files if you're saving out a crowd sequence. So if we were to save out a BGO file that contains an agent primitive, we need to be able to, of course, load that file into a different instance of Houdini and have the agent primitive load successfully. So that means that all of the data that's in the agent definition, so things like the geometry shapes and animation clips and so on, that the agent primitive needs has to be loaded in or has to be saved in with that BGO file. So that has some definite downsides because if we have a sequence of BGO files from, say, a crowd simulation cache, that means that every separate BGO file in that sequence is storing a duplicate copy of all the data in that agent definition. So that's going to be wasting a lot of disk space, causing us some performance issues because we're loading in larger files and so on. So let's switch over to a little example file here. So in this case, I'm just using the stadium example from the crowd shelf, and I've just trimmed it down to be showing a smaller section of the stadium for faster demo purposes. So in this case, if we were to save out a cache of this simulation sequence to disk, so we'll just use the file cache sub, we'll notice that the files on disk are a little bit large. We'll do a before and after comparison after we've dealt with this issue, but our files to start with are about 2.6 megabytes. So if we were to play back this cache, we'll notice that our performance isn't very good. So I'll just switch on the FPS view here, and you'll see that we're getting maybe 5 frames a second when we're playing it back, versus if we're playing back our original just in-memory simulation, we're getting maybe 100 frames a second, which is much better. And so the problem with this is that on every frame, we're loading in basically a new version of the agent definition, because each BGO sequence is just embedding separate data that looks like an entirely different copy. So the viewport isn't able to cache anything and so on. So we're really not getting very good performance. So to deal with this problem, all of the components of the agent definition are able to be marked as external references, basically being flagged as being a reference to a file on disk. So then when we're saving the agent out to a BGO file, it can just store paths to reference those files on disk, kind of like a packed disk primitive, rather than actually embedding their contents. So to set this up, we'll use the agent definition cache SOP, which is the main SOP for dealing with agent definition caches and files on disk. This is actually a wrapper around the agent ROP, which is the ROP for saving out agent definitions. So on the SOP, we have options for which files we want to be saving out. So you can choose whether you want to save out everything or just certain parts of the agent definition. So for example, the shape library is going to be saved out to a BGO file. Each of the animation clips are going to be saved out to their own B clips. The layers are all going to be saved out to some text files describing the contents of the layer and so on. So if I hit save to disk, this will save this out to an agents folder based on this cache directory here, and then a subfolder with the name of the agent type, in this case, mocap iPad 3. And so now we've got all of the B clips for all of our animation clips that we've set up. We have a BGO file for all of the shapes that are in our shape library. And then for things like our rig, we have just a simple text file with describing what joints are available in the rig, what the transform hierarchy is. This is just in a JSON format. And then similarly for layers, we also just have a simple text JSON format describing what the contents of the layer are. And so then once we've got this agent definition cached to disk, we can turn on the load from disk option, and this will reload the agent's definition from disk and flag all of the different parts of the agent definition as being external references. So that then later on, when we're saving out the agent primitives to a BGO file, they can just save those file references in the BGO file rather than actually embedding all of the contents. So then this keep external references toggle is what controls that behavior. So if you turned it off, the agents would no longer be saving out external references in their BGO files. Typically, you would, of course, want to have this on, but if you want to, say, generate a standalone BGO file that doesn't reference any other files on your file system, for example, turning this off can be handy in certain cases. So now that we've turned this on, let's go back to our simulation, and we'll recache this out to disk. So I'll just let that cache, and so if we go back and examine the size of our file caches, we'll see now that they're almost a third of the size that they were before. And so this is a pretty nice decrease in file size. And obviously, if the agent definition was heavier, so we had maybe some more geometry shapes in there, there'd be an even larger difference. So now, instead of saving all of the contents of the agent definition, the agents are only saving sort of their per instance data. So things like what their current pose is, which layers they're supposed to be displaying out of the agent definition, and so on. So our file caches are definitely a lot more lightweight. And so now if I go to play this back, we'll see that we're getting much better playback performance. Our playback performance still isn't quite as good as our playback from the in-memory simulation, though. And so the reason for this is really just the number of frames that are being cached in memory as we're loading the BGO files. So obviously there's a bit of extra overhead from having to load in a BGO file and create those agent primitives rather than just playing back the cache simulation from docs. So typically you'll want to have the cache frame set to at least 1 if you're playing back a crowd cache from disk. And the reason for this is that agent primitives have a cache internally of all of the agent definition files that were loaded from disk, so the shape library and clips and so on. And so this way, if the same file gets tried to be loaded multiple times, this can just use the cache data rather than actually spending time to reload it from disk. So by setting the cache frame to 1, we'll make sure that the agent definition file cache is always staying populated, So that'll really help playback performance. But if we want to match our original in-memory playback performance, we can just set our cache frames to be 240, the range of our play bar. And then this way, once we've actually completed one playthrough, all of the contents will be cached in memory, and then our playback performance will be just as good, or if not better, than what our playback performance was from playing back in docs. So that wraps up the first section with an overview of agent primitives and agent rigs. In the next sections, we'll continue on and dive into more detail on other parts of the agent definition. Thanks for watching.